Hello again. In this lecture we are going to talk about MODFLOW solvers. Whenever you create a MODFLOW simulation, you have to select one of the solver packages, which are shown here in the packages dialog. The default one in GMS is the PCG solver, but as you can see there are a number of other available solvers that you can use. And today we're going to talk about the different solvers and the parameters that are associated with most of the solvers that you need to understand in order to be able to use the solvers. Now, one of the immediate questions is why so many solvers? And the answer is each of these solvers uses a different algorithm to generate a set of heads that satisfy the governing differential equation. And sometimes for a particular model, the solver you have selected will not converge. And so you have to try a different solver. Sometimes you have to keep trying different solvers until you find one that works. So unfortunately, there's not a single solver that is the best solution in all cases. Some of these are more robust than others, but it really pays to have a number of different solvers. Think of these as different tools in your toolbox that in some cases one of them works well, and in other cases you need to use a different one. And most of these solvers use what is called an iterative solution algorithm. And the way that works is, think of this array shown on the right as a set of head values for each cell in your MODFLOW grid. So to begin with, the user provides an initial guess at the head values. In other words, you're trying to guess what the final head values would be, and that provides a starting point. We call these the starting heads. And then what happens is these starting heads are iteratively tweaked until the head differences, as you compare the head in one cell versus the head in its neighboring cells, when those head differences and the implicit derivatives associated with that satisfy the governing equation, then you found a solution to the model. And so what happens is it goes through these heads in what's called a series of iteration. At each iteration, it perturbs the head in each cell in the grid to try to get a better match, to try to come up with heads that satisfy the governing equation. And it keeps doing this. It keeps changing the heads until it converges, until it gets to where the head changes required are smaller than some tolerance. We'll talk more about that later. And each solver uses a different algorithm to tweak or modify these heads over the course of these iterations. And the process involved in each of these solvers, it's fairly complicated. There's a lot of linear algebra involved. Each of the solvers is really well documented, and you can read up on that in more detail if you like. We're not going to go deep into the algorithms used, only to understand in this lecture that each solver has a different approach or algorithm for modifying those heads. And sometimes we need to switch solvers or play with our solver parameters in order to get a model to converge. What does it mean when it doesn't converge? Well, maybe it tries hundreds of iterations and it can't settle in on a solution. The heads keep changing without reaching a point where they satisfy the governing equation. So here are the main solver packages in GMS. The SIP, SOR, these are two of the original solvers that came with MODFLOW. They're quite old. They're still useful, especially the SIP solver. I don't use the SOR, the slice successive over relaxation solver, very much. It's not very stable. That's probably my least favorite of the solvers. The SIP sometimes works well. The PCG solver, precondition conjugate gradient, that is a really solid all-around solver. Therefore, it's the default solver in GMS, meaning when you create a new simulation, that's the one that's selected by default, and it works pretty well. There's a newer version, PCGN, that works well sometimes. There's a Newton solver, NWT. This is only used when you select the MODFLOW-NWT model. And it works really well on wetting and drying problems, and we'll come back and talk about that later. The GMG is a geometric multi-grid solver. Multi-grid solvers, the LMG solver down below is also a multi-grid solver. With a multi-grid solver, it divides the grid into the kind of a super grid. So maybe 50 cells will be considered a single cell, and it solves that, and then it breaks it down into smaller aggregate grids until eventually it's down to the final resolution. These can be really fast, like especially that LMG solver, which is actually a commercial solver. It's actually not free. You have to pay for that one. It's developed by a company out of Germany. But it's the fastest of all these solvers if speed becomes an issue. And then there's an SMS sparse matrix solver, which is used with the unstructured grid version of MODFLOW. And then finally, I should mention the DE4 solver. This is the only one of these that I'm aware of that does not use an iterative solution algorithm. It uses a direct, it formulates a big set of equations and solves them using something like I can't remember the name of it, but a matrix solver. But I haven't had a lot of good luck with that one, but it's there for if you want to try that. Now, for each of the iterative solvers, there are some basic solver parameters that you need to be familiar with. And if you remember nothing else from this lecture, this slide is really important. And one of those solver parameters is the maximum number of iterations. So as I mentioned, you start out with a set of starting heads, and it makes a series of iterations where it attempts to improve those head values until the governing equations are satisfied. Well, there are many cases, as you will find out, where your model is unable to converge. The head values just keep going up and down, and it never converges. And so you have to have a maximum number of iterations. So for example, let's say that number is set to 100. Once it reaches 100 iterations, it will stop and it will say MODFLOW failed to converge. And so I've seen cases where I've had students running a model and their model results don't look right, and we go back and run the model, and the message in the model wrapper at the bottom says it doesn't converge, and they didn't read it carefully, and so they get a set of heads, but it's not a good set of heads because it never converged. It's just some intermediate point. So you need to be aware of what your max number of iterations are, and if it hits it, it means hey, you didn't converge, there's something wrong. And then another fundamental parameter is the convergence tolerance. This is a really small value, 1e to the minus 6th or 5th or something like that. And this is the tolerance that it uses to determine if it can stop iterating And so at each iteration, the solver will calculate the maximum head change at any of the cells. And then it compares that head change to the convergence tolerance. And if the maximum head change is less than the convergence tolerance, it stops iterating and it has successfully converged. And so you don't normally change this. You could make it larger. That's one way to get your model to converge, but usually there are other things we do to get the model to converge, but you need to be aware of that. It's an important part of an iterative solver. And then finally, there's something called the acceleration parameter, and that controls the amount of adjustment made to the heads at each iteration. And as I mentioned before, at each iteration, the solver will look at each cell in the grid one at a time and move the head up or down. It will increase or decrease the head in an attempt to get that cell relative to the adjacent cells to a point where it satisfies the governing equation. So the acceleration parameter, the default value is 1. And what that means is it changes the head by a standard amount that the solver believes is the optimal amount to change it. Sometimes, however, it's not uncommon to have a situation where we get in a state that we call oscillation. You'll look at the convergence graph in GMS, and your heads there's a head in a cell somewhere that's just going up and down and up and down. So it's just moving. It moves too far up and then too far down. Sometimes to get it to converge, you need to reduce the acceleration parameter. So instead of using a value of 1, you can change it, just for the sake of argument, to something like 0.1. So at each iteration, it calculates how much it thinks it needs to move the heads, and then it moves it by 1/10 of that value. And what that does is it kind of slows the solver down. It forces it to use smaller head changes. And in many cases, just doing that alone will allow your model to converge. So that's a really important thing to understand. Now, theoretically, it's possible to use an acceleration parameter greater than 1, which basically says, hey, whatever you think you need to change it even more. I have never encountered a circumstance where that was a good idea. So while it's theoretically possible, I certainly don't recommend it. So it should either be 1 or less than 1. Okay, so what happens when your model does not converge? What are some things we can do to figure out why it did not converge and then fix that problem? So in general, troubleshooting steps. First thing you should do is review the command line output from MODFLOW. That when you run MODFLOW, there's the little window pops up in GMS that we call it the model wrapper, and it echoes the command line output from MODFLOW. And there's information there that can help you get started. First of all, that's how you find out that your model didn't converge. It will tell you MODFLOW failed to converge. And so that's the first thing we look at. Another thing you can do is, hopefully you do this before you run the model, but in case you forget, you can go back and run the model checker in GMS. What this does is it searches through your inputs to find really obvious errors, such as hydraulic conductivity equal to 0 or something like that. So that's or maybe you have a cell bottom elevation greater than the cell top elevation, which can also lead to problems. So that's another thing you can do. Another thing you can do is look in the MODFLOW output file, and when you read a solution into GMS, including a solution that doesn't converge, there's a .out file. If you double click on that, it opens up a text file that is generated by MODFLOW, And that text file will tell you, sometimes have really important diagnostic information. For example, it may tell you which cell has the largest head change, and you can look at that cell and sometimes figure out what's going on with it. So now let's look at some of the things that could cause your model not to converge. One of those could be improper aquifer properties. For example, if you have a hydraulic conductivity of 0 anywhere in your grid, that will cause the model not to converge. It won't even get through one iteration. Or if you have a hydraulic conductivity that is too small, like a really tiny value, that can cause heads to get very large. Suppose you have recharge coming in, that will cause the water to mound and get really large, and that can cause some instabilities. Or if you have a difference in hydraulic conductivity from one cell to the next, too great, could theoretically cause some issues. Sometimes a hydraulic conductivity is too high or too large. That causes a very flat water table, and which could cause parts of your model to go dry. For example, if it made your model dry in a region where water is supposed to be coming into your aquifer, then that could cause your flow budget to become unbalanced and could cause some problems. So make sure you have reasonable K values when you're setting up your model. The same is true for things like recharge and so forth. But speaking of recharge, another common problem is an unbalanced flow budget. In this screenshot here, I purposefully made a model with an unbalanced flow budget, and to show you what the error versus iteration chart looks like. It just keeps going up and down and up and down, and it never converges. And down at the bottom you'll see MODFLOW 2000 terminated without converging. If you build a model that does not have sufficient head-dependent boundaries, you may end up with a water imbalance. So for example, suppose you build a model where you had recharge coming in and you had some wells, and that's it. No other sources and sinks. If the amount of water you're pumping out of the wells is even slightly different than the recharge coming in, that model will never converge. Think of it as it's similar to where, imagine you have a tub and the drain on the tub is open, but if you turn the water on at a rate that's faster than the tub can naturally discharge or empty, then that tub will eventually overflow. It will never reach a state of equilibrium. So that's kind of what happens in your model if you have unbalanced conditions. So typically you want like a drain or a specified head boundary condition or a river or something that acts as an outlet. It acts as a source or a sink that either adds water or takes water out in a manner that balances your flow budget. And so you need to have well-defined boundary conditions and a well-defined flow budget in order to converge. Another issue is your starting heads, your initial conditions. In most cases, if you let your starting heads equal the ground surface elevation or the top of layer 1, you will end up with a stable model, and that is the default in GMS. It does that for you automatically. But in other cases, you have to have the starting heads closer to the final solution in order to get the model to converge. And you can do that either by interpolating head values, or in some cases we can take the solution from a previous version of the model and copy it into the starting heads array to get some head values that are closer. But I've encountered a number of cases where it was necessary to improve the starting head estimate in order to get the model to converge. Okay, another issue we deal with is called wetting and drying. And if you look at the MODFLOW grid on the right, you will see that there are a number of small red triangles. And these are cells that have gone dry. And the blue triangles are cells that are flooded. The head in the cell is greater than the top elevation. But that's not as big a problem as the drying. The cell drying can be a big problem. And with most solvers, if the head drops below the bottom elevation of the cell becomes dry and is turned off. It becomes inactive. And this can happen at any point in the solution process, any part of the iteration process, not just at the end of the time step or the solution. So as it's trying to adjust the heads, if it ends up moving the head below the bottom of the cell, the cell goes dry, and that's it. It stays dry. And so it can cause a cascading problem. So what causes this? We're going to look at 3 different causes: head overshoot, model parameters, and transient conditions. So first of all, head overshoot. Let's suppose that, let's look at on the left here the initial condition. Suppose that we start out with a starting head like this, and we're looking at we're focusing on one individual cell. And there's a bottom elevation and the final head. In other words, if the model were to properly converge, if the final head is just above the bottom elevation, this can be a difficult problem to handle. So what happens is the solver starts out with that starting head and it guesses how far it should move that down, and it knows that it has to move it down, and it guesses how much. So what happens is it may move it too far. And if it moves it so far that it goes below the bottom elevation, then the cell goes dry and it's turned off during the remainder of the simulation. Well, it shouldn't go dry, because if it were to properly solve it, that head would be above the bottom elevation. The only reason it's dry is because the solver moved it too far. So there are a couple of ways we can fix this. One of which is shown on the left, and that is to reduce the acceleration parameter. We talked about that earlier. The acceleration parameter controls how much the solver moves the head at each iteration. And clearly, if you have head overshoot, it's moving it too far. So if you reduce the acceleration parameter, then it takes smaller steps. So there's iteration 1, 2, through 3, and then eventually it solves it. So that's a simple thing to do. Whenever you see cells going dry, the first thing you should do is go in and reduce your acceleration parameter. And sometimes that will completely solve it. Another way to solve it is to improve your starting head estimates. If your starting head is closer to the final head, then there's less chance that you'll have head overshoot. If it only has to move at a small distance, it's more likely to move it the proper amount and eventually converge. So that is another good way to solve it. I would generally recommend trying the acceleration parameter trick first and then improving your starting head estimates. Sometimes you have to do both of those. And in one of our exercises we're going to do in class, we're going to look at a model where we try both of these solutions for a head overshoot problem. Sometimes cells are going dry due to your model parameters. For example, if your hydraulic conductivity is too high, you could have a flat water table, so like on an edge of your model where the water table should be higher, it's just too low. So if the K is too high, the water just moves through the aquifer too quickly, and that can cause where areas where the bottom of your grid is at a higher elevation, you can have cells go dry. Or if your recharge is too low, if you're just not getting enough water into your model, that can cause cells to go dry, so it's a flow budget issue. Sometimes you have pumping rates are too large on your wells, and that can dry out your aquifer. Or it could be a combination of all three of those things. K is too high, recharge too low, pumping rate is too large, or any two of the three, for example. And so how do you fix this? Adjust your model parameters. Tweak that, change your parameters and try again. And sometimes that can fix the problem. In other cases, sometimes if we're running a transient model, I know we haven't talked in much detail about transient models yet, but if you're doing a transient model, sometimes the stresses, maybe you're changing the pumping rates or the recharge, and that can cause the water or the heads or the water table to fluctuate and for cells to go dry. This is particularly an issue for multi-layer models, especially when your top layer is very thin. And so that can make this an even bigger problem. Maybe halfway through your transient simulation, a bunch of your cells go dry when they really shouldn't. So to deal with it, one of the ways to deal with this is there is a lot of the flow packages in MODFLOW have what's called a rewetting option. For example, the LPF package that we're going to be using a lot can have a rewetting option. It's turned off by default, but what it does is, earlier I said, once a cell goes dry, it stays dry. With the rewetting option, it enables the ability for a cell to attempt to become wet again after it's been turned off. Now, why wouldn't that always be on? That's a good question. The reason is that it could cause your solution to be less stable, and it also increases the solution time. It adds an extra level of iteration that it's okay if you need it, but it's something you only want to turn on if you need it. Now, I want to add here, in my experience, the rewetting option in the BCF pack, in the LPF package, I would use that as a last resort because there's a much better solution. The best solution, if you're really struggling with cells going dry, then I highly recommend you try the MODFLOW-NWT version of MODFLOW. It's one of the options in the global basic package dialog in GMS, and it's a special version of MODFLOW that was released in 2011 that one of its main advantages is it works extremely well for cases where you have wetting and drying issues. And so, yeah, if you have a wetting and drying problem, the first thing I would do is I would adjust the acceleration parameter, play with your starting heads. If that doesn't work, and you're confident that your parameters are good, just try out the MODFLOW-NWT package, and that works really well for most cases. It's a really robust solver. Okay, so that concludes our discussion of solvers, and I encourage you to play with the different solvers and parameters, and you'll become an expert in no time.